back to Bluewater Auto Restoration. It's week 17 of 2025, and you know what that means? Another Saturday morning and another deep dive.
That's right. And this week, we're tackling a topic that can be a real headache for a lot of folks, electrical system troubleshooting.
Yeah, it can be pretty intimidating when you pop the hood and see that mess of wires, right?
It definitely can be, but don't worry, we're going to help you make sense of it all.
That's right. We're going to break it down, give you the knowledge and the tools you need to tackle those electrical gremlins.
Because let's face it, every classic car owner has had to deal with electrical problems at some point.
Oh yeah, absolutely. It's just part of the experience.
And too often people jump to conclusions. They see a symptom like dim headlights and they immediately think, oh, it's the battery or the alternator's gone bad.
Right. But it's rarely that simple, is it?
No, it's not. The electrical system is a complex network. Everything is connected, and a problem in one area can manifest in a completely different area.
So how do we even begin to approach electrical troubleshooting? Where do we start?
Well, the first step is to understand the fundamentals of how electricity works, how it flows through circuits.
Okay, so can you give us a quick Electricity 101 crash course?
Sure, think of it like a water hose. Voltage is the pressure pushing the water through the hose. Current, measured in amps, is the amount of water flowing through the hose. And resistance is anything that restricts that flow, like a kink in the hose.
Okay, that's a helpful analogy. So where does Ohm's law fit into all of this?
Ohm's law describes the relationship between voltage, current, and resistance. It tells us that if the voltage stays the same but the resistance increases, then the current must decrease.
So even a small amount of resistance, like a corroded connection, can significantly reduce the current flow.
Exactly. And in a car, that means your components might not get enough power to function properly.
That makes a lot of sense. So how do we actually find these hidden resistances? What tools do we need?
The secret weapon is a voltage drop test.
Okay, tell us more about that.
Essentially, you're measuring the voltage at various points in a circuit to see if there's an unexpected drop somewhere.
Can you give us a practical example?
Sure. Let's say your car is cranking slowly. You'd measure the voltage at the battery, then at the starter motor while someone cranks the engine. If there's a big difference between those two readings, that indicates excessive resistance in the starting circuit.
Ah, so maybe a loose connection or a corroded cable.
Right. And that's where a good digital multimeter comes in handy, or DMM for short.
So the DMM is our go-to tool for electrical troubleshooting.
Absolutely. It allows you to measure voltage, resistance, and even current flow. You don't need a top-of-the-line model. A reliable mid-range DMM will do the job.
And it's important to know how to use it properly, of course.
Definitely. We'll cover some specific testing techniques later on, but getting familiar with your DMM is crucial.
All right, so we've talked about voltage drop testing and the DMM, but let's circle back to the battery for a second. You mentioned earlier that it's not always as simple as just replacing a dead battery.
Right. People often think a battery simply stores electricity, but it actually stores chemical energy, which is converted into electrical energy when needed.
So a battery that seems dead might just need a little chemical boost rather than a complete replacement.
Exactly. It's not always a throwaway situation.
Interesting. So what are some other important things to remember about batteries?
Well, they have three main jobs: starting the engine, powering accessories, and acting as a voltage stabilizer for the charging system.
And I think we've all heard that warning about disconnecting a battery on a running car, right?
Oh yeah, that's a crucial safety tip. Never disconnect a battery on a running car with the alternator still spinning. The voltage spike can damage your sensitive electronics.
Got it. Disconnect first, tinker later. So the battery provides the initial power, but what keeps everything running once the engine is going?
That's the job of the alternator. It generates alternating current, AC, which is then converted to direct current, DC, to power the car's electrical system and recharge the battery.
So it's like a constant power supply, making sure the battery stays topped up.
Precisely. And modern alternators have built-in voltage regulators to control their output, preventing overcharging.
Okay, so the alternator keeps the battery happy, but what about that initial burst of power to turn the engine over? That's where the starter motor comes in, right?
You got it. The starter motor is a powerful electric motor that draws a lot of current from the battery to crank the engine.
And the starter solenoid, that acts like a heavy-duty switch connecting the battery to the starter when you turn the key.
Exactly. It's like a relay, a high current switch.
So what are some common problems we might encounter with starter motors?
Well, they can wear out over time, especially the brushes and bearings. The solenoid can also fail. And even if the starter motor itself is fine, a problem elsewhere in the starting circuit, like a corroded cable, can prevent it from working correctly.
So a simple starting issue could actually have multiple potential causes.
Absolutely. And that's why it's so important to have that systematic approach to troubleshooting that we talked about earlier.
This has been a great overview of the electrical system and some of the key components, but I know we've only scratched the surface.
There's so much more to cover.
So join us next week as we continue our deep dives into electrical troubleshooting and look at some real-world scenarios and how to diagnose them.
We'll be putting all this knowledge into practice.
In the meantime, if you're looking for more tips and resources, be sure to visit BlueWater.CA.
And you can find our podcast on Spotify, Google Music, YouTube, Apple Podcasts, Amazon Music, or SoundCloud.
We'll be back next Saturday with more deep dives into the world of classic car repair.
See you then. Welcome back to our deep dive on electrical troubleshooting.
So last week we talked about the fundamentals of electricity and how those principles apply to the various components in your classic car's electrical system.
That's right, we laid the groundwork.
And this week we're going to put that knowledge into practice, right? With some real-world scenarios that you've probably encountered in your own garage.
Absolutely. We'll walk through some common electrical problems, how to diagnose them, and hopefully give you the confidence to tackle them yourself.
All right, so let's start with a classic problem that I know has given me nightmares in the past. The dreaded click, no crank scenario. You turn in the key, you hear that single click, but the engine doesn't even try to turn over.
Oh yeah, that click of despair. It can send chills down any classic car owner's spine, but before you panic, there's a logical process we can follow to pinpoint the culprit.
Okay, so what's the first step? Pop the hood and start tracing wires.
Not so fast. Before we even grab our trusty DMM, we're going back to the basics. Check the battery connections. Are they tight, clean, any signs of corrosion?
Like that old saying, right? Check the stupid stuff first.
Exactly. A loose or corroded terminal can create enough resistance to stop the entire starting process in its tracks.
Okay, so let's say those connections are pristine. What's the next step?
Time to check the battery itself.
Yeah.
Grab your DMM, set it to DC voltage, connect the red lead to the positive terminal and the black lead to the negative terminal.
All right, got it. What kind of reading should we be looking for on a healthy battery?
You want to see around 12.6 volts. If it's significantly lower, that could indicate a weak or discharged battery.
Makes sense. So the battery tests good, connections are clean and tight, but we're still just getting that click, no crank. What's next?
Now we move our attention to the starter motor and the solenoid.
The solenoid, that's that heavy-duty relay we talked about last week,
You
right?
got it. It acts as a high current switch connecting the battery to the starter motor. And to test it, we're going to use that voltage drop test we discussed.
All right, walk us through it.
Have someone turn the key to the start position while you measure the voltage across the solenoid. Connect your red lead to the positive battery terminal and the black lead to the solenoid's output terminal, the one that goes to the starter motor.
Okay, and what are we looking for here?
Ideally, you want to see a very small voltage drop across a good solenoid. Less than 0.2 volts is perfect. If you see a significantly higher drop, that solenoid is likely the culprit.
So we've eliminated the battery and the solenoid as suspects, but the engine still won't crank? What's our next move?
Now we turn our attention to the starter motor itself, and this might involve getting under the car, so grab your creeper and safety glasses.
Safety first, always. So how do we actually test the starter motor?
We're going to bypass the solenoid and send power directly to the starter motor, but safety first. Disconnect the battery's negative cable. Then, use a remote starter switch or a heavy-duty jumper wire to connect the positive battery terminal directly to the starter's main terminal.
Okay, so we're essentially hot wiring the starter motor.
In a controlled and safe way, yes. If the starter motor is good, it should spin strongly. If you get no spin or a weak spin, that means it's time for a new starter motor.
So we've gone from the battery connections all the way down to the starter motor itself. That's a pretty comprehensive diagnosis for a no-start problem.
And that's the beauty of a systematic approach. It helps you eliminate possibilities and avoid replacing parts unnecessarily.
I love it. Okay, let's shift gears now and talk about another common issue. Dim or flickering lights.
Oh yeah, dim lights can be frustrating, and sometimes even dangerous if you're driving at night. So where do we start with this one?
Well, the first thing is to check the bulbs themselves.
Of course. Right, make sure they're the correct type and wattage and that they're properly seated in the sockets.
Simple, but often overlooked. But if the bulbs are fine, then we start thinking about the wiring and the connections.
And I'm guessing voltage drop testing is going to be our go-to method again.
You got it. This time, we're focusing on the light circuit. Check the ground connection for the light first.
Why the ground connection?
A bad ground can cause all sorts of strange electrical behavior, so make sure that connection is clean and tight.
How do we actually find the ground connection for the light? Is this where a wiring diagram becomes essential?
Absolutely. The wiring diagram will show you exactly where the ground wire for that particular light is located. So consult the diagram and then check that connection for any looseness, corrosion, or damage.
Okay, and once we've confirmed a good ground connection, then what? Then we can move on to checking for voltage drop across other points in the circuit, like the switch, the fuse, and any connectors.
It's like we're electrical detectives, using voltage drop as our clue to follow the trail to the problem area.
That's a great way to think about it. And don't forget to inspect the wiring itself, too. Look for any damage, any chafing, or melting. Even a pinched wire can create a high resistance point.
Right. These are all things we can visually inspect without even needing any fancy tools.
Exactly. A little bit of detective work can go a long way in electrical troubleshooting.
Let's move on to one more scenario. This one is a common one, especially with older cars. A non-working electrical accessory, like a power window or a radio. Where do we begin with this kind of problem?
The first step is always to check the fuse for that circuit. Fuses are designed to protect the circuit, so if there's a problem, the fuse is often the first thing to go.
Always a good place to start. So, let's say the fuse is good. What's next?
If the fuse is good, then use your test light or your DMM to check for power at the accessory itself. We're working backward, from the non-working component towards the power source.
Okay, I see. So if we find power at the accessory, but it's still not working, then the problem must lie within the accessory itself.
Exactly. You've effectively eliminated all the external factors.
I really appreciate how you're breaking down these complex problems into smaller, more manageable steps.
That's what it's all about. Taking the mystery out of electrical troubleshooting and giving you a clear path to follow. And that's what we'll be focusing on next.